Hi everyone, welcome to this session. Actually, in this session, we will try to analyze this circuit in a details manner. Okay, like this circuit. Okay, so for that, we will try to do the step response analysis. Okay, so for step response, so I am drawing the circuit again. Okay, so for step response, what we see, we try to see the behavior of the circuit at t equals 0 plus and t equals infinity. So this is our initial stage and this is our steady state, right? And we are assuming both of the capacitor C1 equal to C2 is C, and both are initially uncharged. Okay, uncharged. Okay, so now what happens at t equals 0 plus? We know at t equals 0 plus the circuit fills a frequency of infinite, right? So at infinite frequency, both of the capacitor is shorted, right? So cap is short circuited. Okay. So if the cap is short circuited, what will be the reduced picture? So this will be nothing but this resistance, and this is short and this is short, right? Okay. And this is our V out. So we can see that this node having two potential. One is this ground 0 volt and another is this V in. But the KVL is violated, right? Because at a node there cannot be two voltages, there will be only one potential. Okay, so actually KVL is violated here. Okay, to comment this voltage. Okay, so what we can do, we know if the capacitor is short circuit, the current through the circuit is infinite, right? Because there is no resistance, because R is 0 here. Okay, so there will be infinite current. Okay, so what will happen, the capacitor will change its potential across it suddenly. Okay, so capacitor can change its potential suddenly. Okay, suddenly or abruptly, because the current here is infinite at t equals 0 plus. Okay, so what will happen, actually there will be a charge sharing concept here. Okay, the capacitor will, like, the initial charge will be the final charge. Okay, and we are assuming that both of the capacitor is value of C, right? So both the capacitor will equally charge, will be equally charged, right? So if we have a 5 volt, so both of this capacitor Vc1 and Vc2 will be 2.5 volt, right? So what actually happening at t equal to 0 is both of the capacitor is short circuit, right? So there can be many interpretation to looking into this circuit. I am telling some of them. As this potential is goes here, so V out will be V in, and again this 0 voltage is going to here, so V out will be 0 volt. But this is not possible, right? The KVL is violated, and we can see that there is a infinite current flows through the circuit at t equals 0 plus. So we can see the potential across the capacitor can change abruptly or suddenly. Okay, so actually at t equals 0 plus, the potential across both of this capacitor is suddenly jumps to 2.5 volt. Okay, so what will be the picture? So if we try to draw the plot at Vc1 and Vc2, okay, so this is our Vc2 and this will be our V out as well. Okay, and this is our T and this is our Vc1. Huh? Okay, and this is our T. So the Vc1, the polarity will be like this. Okay, this is plus, this is minus, and this is our Vc1. Okay, so we can see the potential at t equals 0 plus is 2.5 volt. Okay, so basically previously it was 0 volt and suddenly it jumps to 2.5 volt. Okay, let's say this is 2.5 volt, and this potential also jumps to 2.5 volt. Okay, now what will happen, what will happen so so at and steady state. Okay, now let's say at t equals infinity. So we know the capacitor acts as a open circuit because the frequency is 0, right? So at DC, the capacitor is open circuited. So and we know that actually we are talking about open circuit because of the impedance of capacitor is 1 over S, right? So if this S frequency is 0, then the impedance is infinite. So the infinite impedance means a open circuit. Okay. So no current can go through this infinite impedance. So this will be open circuit. Okay. So then what will be the picture? So the picture will be, so this is our R and this is open circuit and this is also open circuit. Okay. And this is our V out and this is our V in. So we can see that there is no current flow through this resistance. So there will be no drop, no IR drop across this resistance. So basically this resistance is short circuited. Okay. So if there is a no drop across this resistance, the so we can assume that the resistance is short circuit. So we can directly see that the V out is equal to nothing but the V in. Okay. So this is how the circuit behaves. So we can see that and we can see that at steady state the voltage will be 5 volt. So let's say this is our 5 volt. Okay. Now what about the VC1? So this is our V out. Okay. And this was our VC1, right? So what do you think? What is the voltage across this C1 capacitor? Let's say this is C1 and this is C2. This is definitely 0 volt, right? Because this node is nothing but this node and this node is nothing but this node. So this is the same node. Okay. So this is, if this is X and this is Y, so the Vx minus Vy is the same potential and this will be 0 volt. Okay. So basically what happening is at steady state the Vc1 will be 0. Okay. Okay. So basically what happening here is at t equals 0. Okay. So at t equals 0. Okay, let me draw the picture again. Okay. So basically at t equals 0, both of the capacitors charged to 2.5 volt and and after t equals 0 plus, this capacitor actually discharging through this way and this capacitor is charging more. Okay. This C1 capacitor is discharging through the resistance and this C2 capacitor is charging like from 2.5 to up to 5 voltage. Okay. Like fully charged to be in. Okay. At steady state at t equals infinity. Okay. But we know that this like the V out cannot be 5 volt completely, like it will take infinite time. So this is not possible, right? So this will go to 9999 like this. Okay. So it will go to asymptotically to 5 voltage. Okay. So now what will be the waveform? So we can see that after t equals 0 plus, after t equals 0 plus, after t equals 0 plus, there will be a finite current, right? Because there is present a R here. Okay. Right. So the charging will be exponential. We all know that. Okay. So now the capacitor C2 will charge exponentially to 5 volt. Okay. And this VC on, the capacitor C on will discharge exponentially. Okay. To 0 volt. So this is our 0 volt. So this circuit feels like that. Okay. So at t equals to 0, the V out will be our 5 volt and VC on will be 0 volt. This, like this C2 capacitor is charging more and this basically this C1 is discharging and this C2 is charging. Okay. And the C2 will charge fully to 5 volt asymptotically at t equal to infinity. Okay. So this is the insight. Now we will go to frequency response. Okay. Like the Bode, like the poles and zero case. Okay. So we have this circuit. So to find the pole, what we do? What we do? We 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 do the all the independent sources are inactive. Okay. And we see what is the R equivalent and what is the C equivalent, and then we take 1 over R equivalent times C equivalent. Okay, so if this is our V in and this is a voltage source, and if this is inactive, so it will be short circuit to the ground. Okay, now we can see that this is a only one effective node. So what is the equivalent R here? So R is nothing but this R only. Okay, and what is the equivalent capacitance? C equivalent. So we can see that this is a one node, and both of this capacitor having this same node and having this ground node. So both of the capacitor comes in parallel. Okay, so what will be the effective capacitance? So this will be nothing but C1 plus C2, and this is nothing but 2C, because the C1 equal to C2 equal to C, right? So our pole is at minus 1 by R 2C. Okay, so if we write in a better way, this will be 2RC. Okay, and this will be definitely be negative half plane pole. If you write KCL, like if we do Laplace domain, you will get this. Okay, so we have pole. Now the question is there any zero? Acha, before coming to zero, I am doing another thing. Okay, basically we have two capacitor. Okay, so the maximum number of pole can be two. Okay, but here we are getting only one pole. How? Basically this is a, like, the effective capacitance is a single capacitance like this. Okay, and we can see that if we make this as a VC1. Okay, so the if we write KCL KVL, so this will be nothing but VC1 plus VO. So we can see that if we fix this, so this will automatically fix, because this is given to 5 voltage. So basically there is only on state variables. Okay, state variables. Okay, like independent state variable. Okay, independent state variable, so that the circuit is having only one pole, and this is also called a first order circuit. Okay, first order circuit or single pole system. Okay, this is also called first order circuit. So number of pole defines the order of the circuit. Number of poles defines the order of the circuit. Order of the circuit. Okay, here we have two capacitor, but effective capacitance is a single capacitance. Okay, so that the circuit behaves like a single pole system. Okay, and we can also see that there is only one independent state variable. Okay, so now go for the zero. So let me draw the circuit again. So for zero, we know the V out will be zero, right? Actually, V out by V in nothing but some DC gain times 0 by poles, right? We know that. So we know that to make 0, the V out will be 0. Okay, so if we make this V out is 0, this is ground. So for this 2C capacitor, this this 2C capacitor, both of the terminal in ground, so this is out of the picture, right? So there is only on effective branch. Okay, this C1 and this R. So what will be the zero value? Like zero location. So zero location will be nothing but this branch will only contribute this 0. So this will be nothing but, let's say, omega z will be nothing but 1 by R C1. Okay, so this is the 0, and this will be always in left of plane. Okay, if you write the Laplace domain equation, you will find there will be a negative sign. Okay, and I am not going to do that. Okay, so we have pole and 0. Okay, another way to find the 0 is, and okay, so intuitively how we can see if there is a 0 or not? Actually, if there is a sudden jump, at t equals 0 plus. Okay, if there is a sudden jump at t equals 0 plus, that defines there definitely a 0 present. Okay, a 0 present. So we can see that what was our steady at t, yes, so we can see that at t equals 0 plus, there is a certain jump. Okay, across the like the potential across the capacitance. Okay, the voltage across the capacitance is suddenly jump at t equals 0 plus. So this means there is a definitely a 0. Okay, this is the time domain, yeah, like time domain analysis to find a 0. And the second way to find the 0 is, so we can see that if V out is 0, we are having a 0. So we can see that there is two effective impedance path. Okay, let's say this is Z1 and this is Z2. So we can see that this V out can be 0 if this impedance is 0 or if this impedance is infinite. So if Z1 is infinite, then our V out can go to 0, or Z2, if Z2 is 0, then our V out can be 0. Okay, but we can see that there is a only one combination of C2. So this impedance can go to 0 at infinite frequency. So infinite frequency is our not consideration. So that is not possible. So basically for this case there is a 0, but this is at infinite frequency. So we generally say the like due to this C2 capacitor there is no 0 present. Okay, so only way is this impedance can go to, if this impedance can go to infinity, so we can get a 0. So let's do that. So there is a parallel combination of R and C1, right? So what is the impedance here? So we know that R parallel 1 over SC1 will be equal to infinite. So if we do that, R into 1 over SC1 divided by R plus 1 by SC1 will be infinite. So if we solve this, we can see that if this portion go to 0, then this becomes infinite, like this whole term becomes infinite, right? So let's do that. R plus 1 over SC1 will be 0. So we can see that S will be minus 1 by R into C1, and this is nothing but 1 by RC. So this is how we can also get the 0 value like this. Okay, so this will be omega Z. Okay, so now we have find pole and 0. Now we need DC gain to get the Bode plot. Okay, so we need DC gain. Okay, DC gain. So DC gain is what? At DC capacitor is open circuit. So if this capacitor is open circuit, what will be our picture? So this will be R. So this will be open circuit, and this will be also open circuit. So what is our gain? V out by V in. So our V out by V in is nothing but 1, right? Because there is no current flow, so this is short circuit. So our V out will be V in, right? Because this is a short circuit part. So this is a gain of 1, and this is a purely passive circuit, so the gain cannot be more than 1 in linear, right? And if so, and in dB this will be 0, like 20 log of 1 will be 0, right? 0 dB. So DC gain is here is 1. So if we draw the, okay, I will only draw the Bode magnitude plot. Okay, so let's say this is our Bode magnitude plot. Okay, and this is our frequency. So we can see that at DC, so omega equal to 0, the gain is 1. Okay, so this is our 0 dB. Okay, gain is our 0 dB. Now we can see that pole was at omega p was at 1 by 2 RC, and omega z is 1 by RC. So which is the lower frequency? This is the lower frequency, right? So in this case the pole comes first. So let's say here is our pole. So at pole frequency we know the Bode magnitude plot is decreased by minus 20 dB per decade. So let's say this is minus 20 dB per decade. Okay, okay, now we have a 0 here. Let's say the 0 is at here. Okay, so this is our omega z and this is our omega p. Okay, and now this will be like this, right? Because we know that at omega z, like at pole frequency, the slope is plus 20 dB per decade. But because this is falling from minus 20 dB per decade, so if we add plus 20 dB per decade with minus 20 dB per decade, so this will be zero slope, right? Sorry, 0 dB per decade. So this will be 0 dB per decade slope. Okay, so this is how the Bode plot will look like, right? And we can also like this is 0 dB, right? And what will be this value? Can we comment that? So let's try. So we know that at infinity frequency, the at infinite frequency, at omega equal to infinite, the capacitor is short circuit, right? So if the capacitor is short circuit, the picture will be looking like that, right? So if this is a R, okay, so this is our V in and this is our V out. Okay, let me comment on in transfer function. Okay, so we have DC gain, right? So DC gain, so V out over V in of S is nothing but DC gain is on times 0 on plus 1 by omega z divided by 1 plus 1 by omega p. So if we do that, so this will be on. So now we have to make the S is infinite. Okay, so how we can make that, right? No. Yes, we have to make S equal to infinite, right? So that we can find the gain at infinite frequency. Okay, so if we do that, so can we comment the gain? Okay, on think 1 minute. Okay, I will do it later. Okay, in another video. So it will take time. So now we have analyzed the circuit in a in a deep manner, and for time domain mathematical expression. For mathematical expression, we know the voltage across a capacitor with respect to time is nothing but the voltage across a capacitor at infinity uh, uh, plus Vc of 0 plus minus of Vc of infinity times e power t by tau, right? So here tau is nothing but 1 by 2 RC, and this is nothing but 1 over omega p, right? So this is how you can also mathematically comment this Vc voltage at any time instant. Okay, so at any time instant. Okay, so what we have seen that, so we know that the Vc of infinity is nothing but like the V out. Okay, here is the V out. Okay, so V out at infinity is nothing but hot. So this will be 5 voltage, right? And we have find that V out of 0 plus is nothing but 2.5 volt, right? We have find that because this will suddenly jump to 2.5. So if you put that, so V out of t will be nothing but 5 volt plus 2.5 volt minus 5 volt into e power e power t by tau. Okay, so tau is 2 RC. So if we put at put this time to find the to find the potential line the to find the V out with respect to time, so you can put the time here and you will get the the V out voltage at any time instant. Okay, and we have seen that this will jump to 2.5 volt and then it will reach to exponentially to 5 volt. So let's put here, so if this t equals 0, so this will be 1, and so this will be minus 2.5, and this is 5 plus 2.5, so this will be 2.5. So from the equation we can also find that. Okay, and if you put t equals any number, you will get this type of voltage. Okay, at any time instant. So this is the mathematical expression. Okay, and okay, so how to find the Vc one? Okay, so basically this is discharging, right? So discharging equation is nothing but Vx, let's say this V of 0 plus time e power t by 2 RC. Okay, like t by tau, and it will be V 0 plus, okay, Vc1 of 0 plus time e power t by 2 RC. Okay, so this is how you can also find the potential at Vc1 at any time instant. Okay, so this will be jump to 2.5 volt and it will finally exponentially decaying to 0 voltage. Okay, so basically this is the discharging equation of a capacitor and this is the charging equation of a capacitor. Okay, so you need to remember this. Now what I can say about this circuit, so this is the main thing. Okay, so you can do for this ramp response. Okay, you can do the impulse response. So okay, so it will build your intuition and you will feel the circuit in a more convincing way. Okay, okay, basically this circuit is many times asked in the interview. Okay, so that I am doing, I have done this. Okay, so okay, so we will tell more insight for this circuit. Okay, thank you.